Good evening and welcome to the Chemistry A2 live session for the spring 2024 season. I will be transferring you across to Mr. Black now, who's responsible for 2 of the 4 sessions that you've previously tuned into. But just before I pass over, kindly remind you that there is that Q&A button at the top. If you do have any questions during this live session, then one of us will make every effort to address that question in due course. Over to you, Mr. Black.
Okay, thank you very much. Okay, so if you were on the previous sessions that were recorded, you would have seen my session 1 and 3. So we've got the accurate entropy change calculations and then the iodine clock, and specifically looking at mechanisms, always a tricky thing. So we'll start with this session 1 then, accurate entropy change. Okay, now here I've gone straight into using entropy changes in Hess cycles. The actual practical technique of measuring the entropy change is really important, so please make sure that if you haven't seen that video about how that's done, then you go and have a look at the Cymru resources, because it will be there, session 1 2024 spring. Okay, so here's a question then. Again, WJC, they put lots and lots of writing in here, and you've got to find the information that you need. So if I have a quick look, we can see here that we're, first of all, given this reaction between calcium hydroxide or calcium hydroxide decomposing into calcium oxide and water. You can see here it uses the term thermal decomposition. And it says we can't measure this entropy change directly, so this is where Hess's law comes in. Okay, so we will be given an entropy change in a moment. I don't think it's on this page here. No, it's not. We're going to be given an entropy change for the reaction of calcium hydroxide and hydrochloric acid. But we're going to have to work out an entropy change ourselves, and that's the reaction of calcium oxide and hydrochloric acid. So you can see here in the question, they've given you a mass of calcium oxide and have told you the temperature change. Okay, and what you're being asked to do, first of all, here in the first part of the question, is to work out which of these reagents are in excess. Okay, the calcium oxide, the hydrochloric acid. So what we'll do then, we'll work out the moles of hydrochloric acid first of all. Okay, so you can see here it tells us some important information about the hydrochloric acid. We're going to use our formula triangle, CMV, concentration equals moles over volume. And we've got a moles of 0.07 mole hydrochloric acid. Now you're going to see why it's really important we know who is in excess. I think I mentioned this on our previous presentation. We'll work out the moles of calcium oxide next. Okay, so you can see here we've been given a mass of calcium oxide. This is going to be our mass over MR. Okay, and those are the number of moles that we're using now. At this point, I mentioned this yesterday, please don't assume that you're done. You're not done there. We need to look now in terms of, well, how many moles of each thing do we need? And this is where we're going to have to refer to our balanced equation for the reaction. So we know the moles of calcium oxide, and we know the moles of hydrochloric acid that we've got. So let's look at the reaction. I'm just going to put the calcium oxide moles there. And if you use the stoichiometry, hopefully you'll be able to tell me or work out for yourself how many moles of hydrochloric acid there are. Okay, so you can see it's a 1:2 ratio. So the moles of hydrochloric acid needed is actually double the moles of calcium oxide. Now, if we look at what we've worked out, we can see here that actually we've got 0.07 moles. And so the hydrochloric acid is in excess, because from our calculation here, we need less than that. Okay, so if you want to show it's in excess, you're going to have to work out the moles of both, and then you're going to have to work out, from the balanced equation, how much you need of each. Okay, and we can see there, that's how I'd answer the question. We only need 0.667 moles, and we've got 0.07. So fairly basic, straightforward year 12 chemistry, but that's the sort of stuff you may forget. Okay, so why is it important we know who's in excess? Well, we're going to calculate the energy released in the reaction between the calcium oxide and hydrochloric acid, and we'll work that out, go on to then work out an entropy change. Okay, so how do we work out the energy released in the reaction? Okay, well, that's our formula there. No, you don't get it on the data sheet. You're expected to remember it. Make sure you know what Q refers to. M, C, and delta T. So M is the mass of the solution, because technically 1.4 molar hydrochloric acid, if you were to make that up, you'd have 1 litre of water, and in that you would dissolve 1.4 moles of hydrochloric acid. So in effect it is, 50 centimeters cubed. So our mass here would be 50. Remember, don't include the mass of any solids in this, okay? So for example, you would not use the value of 51.9 for the mass, because we don't include the mass of calcium oxide. It's literally the mass of the water, i.e. the acid. All right, so let's calculate Q. So we've got our mass of 50, we've got our temperature change of 20.5 degrees C, heat capacity 4.18, which you'll get off your data sheet. And you can see here that answers in joules, and that's because our heat capacity is in joules. Okay, right, what's next? Well, we're going to have to work out the enthalpy change. Okay, so to work out the enthalpy change for the reaction, what we need to do is we need to convert that into our energy change into an enthalpy change. And what we've done here, first of all, is divided by moles of the reagent to scale it up to per mole. Okay, and then the minus Q, this is to reflect that, and I haven't mentioned this before, it's to reflect that if you have the energy of the surroundings increase, the enthalpy of the system's gone down, okay, i.e. delta H is negative. So there's our calculation. Now what we need to do here is decide we're going to go for the moles of HCl or the calcium oxide. So I'm just going to let you consider that. Remember, we've worked out the calcium oxide wasn't in excess and HCl was. Okay, so obviously we're going to divide by the moles of the calcium oxide. That's to make sure we get all the energy out from the calcium oxide. Okay, so that gives us minus 126,760 joules per mole, and we'll obviously convert that into kilojoules per mole. Okay, so on the next bit of the question then, this is where we start to construct our Hess cycle. So fairly easy to do. The whole question here, they've given you this enthalpy change here. Mole enthalpy change for the reaction between calcium oxide and hydrochloric acid is, and you've just worked out the enthalpy change when you add hydrochloric acid, calcium oxide. Okay, so that's why I've put HCl there to just say, look, these arrows represent what would happen if we had hydrochloric acid to both calcium hydroxide and calcium oxide, and we get these intermediary products, the calcium chloride and the water. Okay, and we've got our enthalpy values. So we've got this enthalpy change that they've given us, the minus 196, and then we've got this enthalpy change here that we've calculated, minus 126.7. Obviously, it's really important here that you show you're working out in case you made a mistake when you've worked this value out. They can do error carried forward. So there's our Hess cycle constructed. Just a little pause for you to work out the enthalpy change for this reaction then, this arrow. So remember, we're going to go an alternative route. So we're going to go with the arrow, then against the arrow. Now there's two ways you can show the calculation. Okay, you can do that, which is my preferred method. It's a bit numpty, but it's the way I like to do it. Minus 196 plus the 1267 because I'm going against the arrow. Or, mathematically, we could have written this as that's exactly the same thing. Okay, remember when you go against an arrow, you take away the value. Okay, although there's a little printing error there because that should be minus 126.7. So apologies on that. Okay, so that was the calculation done, and then just very quickly it talks about the improvements we can make to this experiment and to give a reason. So obviously, first of all, 1 degree thermometer isn't going to really cut it. Okay, you can see here I've got much better equipment. So the thermometer, first of all, should be accurate to 0.1 of a degree, and that would give you less percentage error, so you can quote more significant figures. And then the polystyrene cup there is to stop heat escaping to the surroundings. Okay, we want to measure that heat, not allow it to be lost. So yeah, good technique here is to use polystyrene cup. It's nice and insulating, and of course don't forget to always have a lid on. Okay, right. So that brings me on to session 2, where we looked at the iodine clock reaction, initial rate and mechanisms. Okay, so there was our iodine clock reaction. And if you remember in this actual practical, we talked about having a constant volume. And, you know, basically what we'd have to do there is we'd have to add water. So we get an overall constant volume of 50 centimeters cubed. Now, actually, funny enough, I've been talking to my year 12s about this recently. And it's not just actually that it allows the change in volume to be proportional to the change in concentration, which it would be, you know. So basically, if you double your peroxide, you're doubling its concentration. There's something actually even more important than that. Makes it a fair test, which I hadn't really thought about, to be honest, until I did. So what does that mean? Well, basically, if we don't actually have a constant volume of 50 centimeters cubed, let's say we were adding this water in, the overall volume here comes out as 50 centimeters cubed, and the overall volume here would only come out as 46 centimeters cubed. So technically, with a lower volume, you've technically increased the concentrations of the sulfuric acid, the thiosulfate, the potassium iodide. And to make this a fair test, you know, if we're looking at the effects of the peroxide concentration, we'd want the concentration of all the reactants to be the same on each run. Okay. Other things to make it a fair test, of course, same temperature. Okay. But yeah, so something I didn't mention on my previous presentation, the idea that, you know, I did say changing volume is proportional to changing concentration, but also it's really important that you talk about or have that idea about this being a fair test by having a constant volume. Okay. Right. So yeah, there we go. So let's have a look then at some questions to do with rates and mechanisms. I thought this was a really interesting question, actually. And when I did this question, I can't remember which year this is, I got it wrong. Okay, it's because I wasn't really reading the question. I wasn't using the information that's available to me. And then as soon as I, you know, read the question properly, I was like, oh wow, that's actually really quite a good question. So it says the reaction is found to be first order with respect to iodine methane, has a rate constant of a particular temperature. Write the rate equation for this reaction. So of course, what I did was I wrote that. And then when I looked, it was like, no, that's wrong. And I realised my error. Now, first of all, what I thought was interesting, and I kind of knew something was up when I looked at how many marks it was available. 2 marks for writing that. Doesn't seem right. Okay, so there must be something else going on here. And then I realised what it was. It's the units of the rate constant. Okay. Now you need to be able to work out the units of rate constant. Please make sure that's something that you can do. All right. I do kind of mention it briefly, but if we have a look here, we can see the units of the rate constant matches this one here. Okay, it's a bit weird how they've written the units. Have put M, that stands for the moles per decimeter cubed. Okay, and then you've got your unit of time there. Okay, so this unit here, okay, mole to minus 1, dm to the 3, s to the minus 1. This is actually a second order reaction. Now at this point, the iodopropanone is what is it? The iodomethane is it's coming out as first order, total order of the reaction. And we see from the rate constant here, the units, this is actually second order. There's only another reagent, okay? That means that we have to have the thiosulfate in there. So that's a really, really good question. I like that. You know, I like it when I get caught out. So rate equations there. And just talking about the units just very quickly, you know, when you're rearranging to find K, you're taking these concentrations over to this side. So we're going to be dividing by, which you can see here. And I've done mole to the 2, okay, dm to the minus 6. And then these cancel out, okay. And then you get the mole at the bottom and dm to the minus 3 at the bottom as well. So that's why we end up with mole to the minus 1, dm to the 3, s to the minus 1. So definitely make sure you can write the units of K. And yeah, it was a good question because it uses units of K to help us write the rate equation. Okay, so another question then, just very quickly, we've got this reaction of N2O5, okay, And what I'd like you to do is just very quickly look at the rate data there and tell me the order with respect to the N205. So hopefully you can see that straight away. This would be a good one to look at, the 4 and the 8, double the concentration and the rate's doubled. Rate proportional to change of concentration tells us that N205 must be first order. Okay, so the next part of the question then says, okay, you've got the rate equation. What's the mechanism, which is what we're going to kind of do a bit of work on. So we've got two possible mechanisms, mechanism A, mechanism B, and you should know how the order of reactant relates to its part of the mechanism. And if you are first order, you will only have one molecule of you involved in or before the rate determining step. If you're second order, there would be two of you in or before the rate determining step. And that doesn't mean in one step. It could be, if your rate determining step is further on in the reaction, then, subsequent steps can be added up. Okay, so we know our N205. Oh, and if you're zero order, by the way, you come after the rate determining step. So the N205 is first order. It has to be mechanism A. It can't be mechanism B. If it was mechanism B, the order of the N205 would be second order. So fairly simple question. So my answer there would be mechanism A. Being first order, there can only be one molecule of N205 in or before the rate determining step. The other thing that I want to do as well, which I quite like doing, is being able to write the balanced equation for the reaction from a mechanism. So I've done this for both mechanisms to just see if it actually matches the balanced equation for the actual process. Okay, so this is reaction here, and hopefully our mechanisms will work out like this. So how do you write a mechanism based on, how do you write a balanced equation based on the mechanism? Well, the first thing we need to do is we need to identify our intermediates. So intermediates, remember, are things that are generated but then consumed in subsequent steps. So I'm going to let you have a quick look now and see if you can work out your intermediates. So hopefully you saw the NO3 dots. That one sticks out like a sore thumb. Okay, so it's generated in step 1 but then consumed in step 2. Any more intermediates? Okay, well, hopefully you spotted the NO dot there. Okay, so it's consumed, generated in step 2 but consumed in step 3. And what does that leave us with? Okay, well, what we're going to do now is we're just going to look at, there's no more intermediates here. Okay, so what I'm going to do is I'm going to write the balanced equation now based on what we've got left. So there's our reactants to N205. Yeah, looks good. And then we've got our products. So I've got NO2, O2 and free NO2. And when I wrote that down, I was like, oh, hang on, that doesn't match. Well, it does. NO2, free NO2, 4 NO2. Okay, so here are my products, NO2, O2 and free NO2. Works with mechanism B as well. So really, if you propose a mechanism, it should match the balanced equation. So there you can see our intermediate. I'm just going to go back there so you can see it. There's the NO3 dot. It's a free radical. Hopefully you recognise that free radical idea. And you can see that this step 1 generates 2 free radicals. Okay, one's consumed in step 1, and then one is also consumed in one's consumed in step 2, and the other's consumed in step 3. So yeah, the NO3 dot's a free radical. We can get rid of that. Any more intermediates? Well, yeah, I think so. We've got this N204. Okay, generating step 1, consumed in step 2. Any more free radicals? Yeah, I think there's another one. So we've got this NO free radical as well, generated in step 2, consumed in step 3. What does that leave us with? Okay, well, that leaves us with 2N205, nothing else as a reactant. They've all been wiped out as intermediates. And then we form the 4NO2, 2 there and 2 there, and O2. So yeah, it works. Okay. Next question then, rate equation for the decomposition of dinitrogen pentoxide to form oxygen nitrogen dioxide is first order overall. Write the rate equation for this reaction. Okay, well, what I've done here is I've written the balanced equation, and it's, the rate equation is very easy to do here. You can see it's only 1 mark, which is rate equals K, and then the concentration N205. Now it says suggest a rate determining step for this reaction. Okay, so this is quite a common thing to be asked to do, and so let's just have a quick look at this. If you remember, I said earlier, if you're a first order reactant, there's one molecule in or before the rate determining step. So what I'm going to do for my rate determining step is I'm going to have one molecule of N2O5. And then what I've done is on the right hand side, I used to say to my students, I just write intermediate, so they'll let you off with that. On the last time I saw this kind of question, they didn't let you off with that. You had to actually put something sensible on the right hand side. And by sensible, it just literally has to balance to the left hand side. I.e. what I mean is I've got to have 2 nitrogens and I've got to have 5 oxygens, which is what I've done here. So, you know, that would be a sensible rate determining step. Or, you know, again, I could do this. I mean, technically, nothing wrong with that. Okay, I've got 2 nitrogens and 5 oxygens. So my left-hand side, right-hand side balances. You know, you can literally come up with some absolute nonsense as long as it balances. Okay, and as long as you've got the one molecule in the rate determining step. Okay, there we go. Good. I just thought we might look at the subsequent step as well. Quite like doing these mechanisms. So if you look in, I'm just going to go with this proposed mechanism here. Okay. If you look at my proposed mechanism, what I've got is in the first step, I've actually produced one of my products. Okay, so there's the half O2. And then you can see these two things. Well, they definitely can't be, they're not products. All right, so these are going to have to be intermediates. So what I'm going to do in my subsequent step is I'm going to write those as 2 intermediates, and I'm going to use them to form the other product. Okay, so there, you know, write mechanisms from rate equations. It's not the easiest task. I always tell my students it's the last question you do, but they are quite fun once you get your head around them. Okay, and then just, you know, come towards the end, make sure you know about this idea of quenching reactions. This is something new in year 13. It wasn't taught to you in year 12. You know, you talked about gas collection, clock reactions, blah, blah, blah. Quenching is a technique, remember, where you have to take a sample at regular intervals, and then you have to stop the reaction. And the way you stop the reaction is by adding a lot of water to it. Okay, and the reason that is called quenching is basically you stop the reaction in its tracks. You've diluted it massively, and then that allows you to carry out titrations so you can determine the concentration, whatever you're looking for. So what's meant by quenching? Taking samples at regular intervals, adding to a large amount of distilled water to stop the reaction proceeding further so that titrations can be carried out or the sample analysed. Okay. And then, you know, if we were going to do this with a reaction that produces iodine, what's a suitable one method of measuring the concentration of sulfate ions in solution is by titration with a solution containing iodine. A suitable indicator with iodine, yeah, it's going to be starch. And then finally, just make sure you're aware of this term homogeneous catalyst, and that's basically where your catalyst is in the same phase as the reaction mixture. Okay. Remember, heterogeneous is where you're in a different phase or different state. Okay, so I'm going to eat into the time for the next session a little bit, so hopefully they won't have too much to deliver to you. So you can see here's another question then, this reaction between carbon monoxide and nitrogen dioxide. And we're being given the rate equation, and you can see here that the NO2 is classed as second order. Okay, so it says explain the term rate determining step. So it's the slowest, most difficult step in a reaction mechanism. And it says, given your reasoning, state which of the above 2 stages of rate determining step in this reaction. Okay, it's got to be step 1. And I'll explain why, because if it's step 2, then we would also see the CO in our rate equation. So our rate equation would be written as rate equals K NO2 to the power of 2 CO, first order. Okay, so, you know, the various ways you could answer that, you could literally talk about that, or you could just say only the NO2 appears in the rate equation, the CO comes after. Is it in the rate isn't the rate equation, so must come after the rate determining step, anything along those lines. Okay, and then just very quickly, we've got this some rate data here. And it says determine the order with respect to the NO2 and the order with respect to the carbon monoxide, and then state that rate equation for this reaction at 600 K. Okay, so using our rate data, who's best to look for? Go straight for the carbon monoxide here. Look at this the same. This one's doubled, rate's doubled. So the NO2 must be, sorry, the CO must be first order. And then I think I'll probably use this run here for the nitrogen dioxide, the double the nitrogen dioxide, kept the CO the same, and we can see again first order. Okay. So rate equation is that. Okay. And then just making sure you can work out your rate constants. Really easy to do. All you need to do is pick one of your lines. Okay. So what I've done there, I've just basically written out the rate equation, and then we're rearranging it to find K. So we're taking our concentrations across. And then I'll do, like I say, pick one of these lines. So I'm going to pick the first line. We plug our values in, and we get our rate constant. You can see there again, it's a second order reaction. So we've got our units of mole to the -1, DN3, S to the -1. And so we're going to go to finally a rate determining step which fits the equation. Okay, so you can see there I put intermediates. If you're struggling, we'll do that. Okay, it's not ideal. I guess if I was going to say what the intermediate might be, I'm going to go CNO2 or CNO3. Is it wrong? Yeah, it's absolute rubbish. Does it balance if I put CNO3? Yeah, so they can't mark it wrong. So there you go. A little bit longer than I was anticipating. I hope I haven't eaten into Miss Stevens' time too much. And I'll start passing you over to her while she sets herself up.
Thank you. Right, just to get my own presentation up.
So I need to come in as well.
Okay, so hopefully you can see there that the two sessions I covered myself were on the enthalpy and the Born-Haber cycles, along with the approach to Unit 5 assessment. So I covered the tips and the approach that most people take to construction of Born-Haber cycles within my session. So if you need to go back and revisit that before this quick recap, then that might be sensible. But what I've got here is just a few questions that might just focus on a few key points. So it says there that this question, why would you suspect the silver chloride is insoluble in water based on the enthalpy stated there? Well, we know that to make a solution, you have to carry out two distinct processes, which is, of course, you have to break that lattice, and then you have to hydrate those ions. Okay. Now, what was potentially misleading in this one is that they gave you the enthalpy of the lattice formation, but obviously that is stated as an exothermic process. But in order to dissolve the salt, you would have to, in fact, break that lattice apart. So you'd be the opposite of that. So it'd be the endothermic equivalent of the lattice formation. And if you can see, based on that, then if I just quickly highlight that, then we know that therefore that to break the lattice, you will in fact need to input 905 kilojoules per mole. Now, even by hydration, which is an exothermic, okay, process, you would not get sufficient exothermic energy repaid by hydrating the ions you form by breaking apart, which is an endothermic process of the lattice. Okay, so don't forget that the solution requires two distinct processes, which is the endothermic breaking of the lattice, as opposed to then the exothermic process, which is the hydration of those ions once formed. Okay, so as is my approach when I do these sessions, I always follow with the next slide with the mark scheme. So feel free to pause before you looked at the mark scheme. It's always good to attempt it, and then you've got a real good sense of whether you've understood it or not. Okay. And then the next question is asking you to calculate a satellite enthalpy of formation of potassium dichromate. But let's focus on this type of question, which is the fact that they have given you clearly the formation of the products as well as the reagents. So, sorry, not the reagents, the reaction itself. Now we know that the delta H of the reaction is going to be the delta H formation of the products, take away the delta H formation of the reactants. Okay, so being that you've actually been supplied with all of this data, as well as this data here within either the tabulated data, or as you can see here, they've given you the overall enthalpy of reaction. A simple rearrangement of that equation, you should be able to work out the formation enthalpy here. Okay, the only loophole and the type of trap I would envisage that you might fall into is the fact that my own pupils included sometimes forget to include the fact that the stoichiometric ratio. So you must, for example, multiply 1,382 by 4 and the dichromatic there, the Cr2O3 by 2. Okay, so don't forget to include them. So if you look at the mark scheme, this is the reason for this and this there. Okay, so it's simple rearrangement of the formula, but do not forget to include the stoichiometric ratio given to you in that balanced equation, because obviously it needs to be considered within that. There was a second question there, which is calculation of the minimum temperature. I'm not going to dwell on that because I want to get on to my second session, which is the approach to Unit 5. But again, feel free to pause and attempt that question when you've got a bit more time. Okay. There was another question then about the standard enthalpy changes to find the standard enthalpy change of lattice. This is the kind of classic question where they give you specific data and they then ask you to construct a Born-Haber cycle. Okay, the first thing before you can approach it, so it's kind of a scaffolded one. Before they ask you to construct it, they ask this question here, which is, say the enthalpy of atomization of chlorine. Well, if you look at this data here, they've told you that the bond energy of a chlorine molecule is 242. Okay, and therefore the enthalpy of atomization of chlorine would be half of that value. So in that sense, it would be 1, 2, 1. Okay, and then it's a case of trying to build together the Born-Haber cycle. Now, I'm not going to write it out fully potentially because I'm renowned for being a bit lazy in that sense. But if I take you through the classic kind of stages, if you start with the two reagent, which is Na, and obviously you only need half a molecule of chlorine, okay, I tend to then break it down into one single function each step. So the first thing I'm going to do is take my solid sodium and I'm going to turn it into gaseous. Okay, nothing else changing, so don't touch that half of chlorine. I'm then going to ionize it to take it to Na+. That is then finished on the process I need for sodium. I'm then going to go back and deal with this chlorine that I haven't quite dealt with yet. So I'm going to take that chlorine and atomize it. So Cl from half of Cl2. I'm then going to turn that into its ionic form, so Cl-, and then I can combine them both to make the product NaCl. So we've got two possible pathways there. As is always the case, clockwise equals anti-clockwise. So by inputting the numbers then from the table given before, you've got 109 for that one, 494 was specified as that one. Remembering to halve the bond energy of chlorine molecule, so 121 minus 364. And the entire delta H of the reaction was specified as being minus 411, which means you've only got one unknown arrow from all of that. So following the clockwise equals anti-clockwise, you can actually identify this value, and it comes out to be, by rearrangement of the arrows, would come out to be minus 771. Okay, which is obviously an exothermic reaction, making it likely to be very feasible. Okay. There are a bit more that you can test yourself on when it comes to the second session. So the first session I ran, which was the Born-Haber and enthalpy session. And feel free to pause and go through all those questions and then check yourself and check your own understanding following your attempt. Okay, but I'm going to go on to this session, the fourth one I did, which is the approach to the Unit 5 assessment, just because we've got some key information that obviously now it's been shared and hopefully distributed to you as A2 students throughout Wales, is that you now have obviously the information of the pre-release to work upon. So as I did in my session itself, let's remind you of that very important resource, which is experiments on film, okay? But then look at this pre-release. So this hopefully has been shared with you already by your teachers or your tutors in your establishments, so your schools or your colleges hopefully have shared this. So we now know that the experimental task, that first task in May, is going to be based upon a thermometric titration, as well as a qualitative inorganic analysis. So the two practical, physical aspects of that assessment for Unit 5 will be based on those two. And then the practical methods and analysis task, 2 days later or a day later, the written paper, so we say, is going to have the following topics incorporated into it, which is electrochemical cells, redox titration, as well as an organic functional groups based question. Okay, so focusing on these, because obviously these are going to be based upon elements of work you did in the lab books. So the first one there, the thermometric titration, I'm hoping that you've all had some hands-on experience with that already. Okay, so this is a typical example of how it would be carried out. So practice for my own students a few weeks back. So you titrate the sodium hydroxide solution with hydrochloric acid by measuring the temperature change each time a portion of acid is added. Then you as students can then determine the end point of that titration, which is indicated by the highest temperature. You then use that information to calculate the concentration of the hydrochloric acid. So make sure you are confident about exactly what steps you need to carry out on that day. And then most importantly, how you would use that data that you acquire in order to achieve the end goal. Okay. So it usually takes about an hour to carry out standard thermometric titration in the required fashion. And don't forget that you should be carrying out risk assessment for your own safety on that day as well. So this is the kind of procedure and the apparatus that you'd be familiar with, hopefully, and the kind of method. So I'm not going to read through all of it, but please make sure that you do, and that you therefore have, hopefully, some confidence that you know exactly how to carry out each of those steps, and also, and very importantly, why each of those steps are carried out in the way that they are. Okay, now the main concern in this experiment is the heat loss, as we all know. So if possible, a lid should be used, but you could also get more reliable results in such a titration by using 2 polystyrene cups. Sounds strange, but it's not unheard of for you to put 1 polystyrene cup inside another, because that will limit the loss of heat to the environment, which obviously will make your data much more reliable. Okay. It is essential that you understand also the importance of extrapolating the cooling curve backwards to estimate the maximum temperature reached without that heat loss, because even if you are careful and use things like 2 polystyrene cups or the lid, if it's feasible to do so, there will undoubtedly be some heat loss in the environment. You can't limit it entirely. So analysis then would require this extrapolation of your data so that you have a sensible maximum temperature theoretically that would have been achieved. Okay, so make sure that you are superbly confident in a thermometric titration and you know how to carry it out and how you'd use that data to achieve the goal or the aim. The second one there was the identification of unknown solutions by qualitative analysis. So I'm focusing on this one because if you carry out a method to identify 6 inorganic salts, I think this was potentially the second practical in your lab book. I think it was from memory. I think the first one was gravimetric, wasn't it? So the second one, if you remember back to that lab book in year 12, which hopefully you're revisiting regularly anyway, you asked to differentiate between those inorganic salts. But at its core, this type of practical was actually focusing in on your knowledge of 1.6 and centres quite a lot on the varying solubilities of the certain salts, as well as their colour. Okay, so we know from unit 1.6 in year 12 that the hydroxides become increasingly more soluble as you descend group 2. We know that the sulfates are the counter arguments, so they become progressively less soluble as you descend group 2. The carbonates are all insoluble, of course, and the exact opposite of the flip argument again is that the nitrates of group 2 are all soluble. Okay, so based upon that, you should be able to work out what the products of each mixture or cross-referencing would produce. And if you haven't already carried it out or you haven't written it up, this is what the model answers should have resembled. So by mixing, obviously, these are mixing with each other, so you can carry that out. So you can ignore the diagonal version there. But for example, if you mix barium nitrate with lead nitrate, you'll get no change because you get 2 soluble salts produced. But if you mix magnesium sulfate, then you'll get a white PPT produced. If you mix it with potassium iodide, you'll get lead iodide, which is that classic canary yellow precipitate. And based on that, you'll notice here that all of the columns will give a slight, distinct, different product or set of observations, and that will then enable you to identify which solution is which, of course. And then moving on to that experimental analysis paper, the second component of Unit 5, which will be the written paper you carry out after the practical element, a day or two later. I'm just going to quickly draw your attention to the, well, one of the final-ish ones that you would have carried out. Hopefully, you've had an opportunity to do so in your centres. My pupils certainly did plan this experiment. We haven't quite got round to carrying it out yet, but we certainly have practiced some of the key techniques. For example, they've done the Tollens test, etc., and the 2,4-DMBH observations. So hopefully you've at the very least planned this sequence of tests, because don't forget, this is going to be theoretically tested, not practically tested in May. So it was designed to enhance your understanding of functional group behaviour and to strengthen the linkage between theory and experiment of a lot of the content in Unit 4, of course. So the key thing I encourage my pupils to do is, before you do anything else, let's identify what the class of compound is. So we've got the amine there, followed by an aldehyde. We've got a carboxylic acid. We've got a methyl ketone. Now, this is key because we have another ketone, but not a methyl ketone. It doesn't really matter what the other ketone was, as long as it wasn't a methyl ketone. We've got an amide and we've got an ester, followed finally by a nitrile. So then you needed to come up with some sort of sample plan of attack. And this is what we eventually came to the conclusion of with my class this year. So that we started with the first thing, which was, let's just test all of them with 2,4-DMBH. We know that will enable us to isolate the aldehyde on both ketones because they will give a yellow or red precipitate and the other compounds cannot. So let's focus then on those 3 that gave a positive test and put the others that gave a negative test to one side for now. So based on the 3 that gave a positive 2,4-DMBH result, you can then further test them with Tollens, and that will then enable you to identify the aldehyde, because that aldehyde will, of course, give a silver mirror, while the 2 ketones do not react. Okay, and finally, to differentiate between the 2 that gave a positive initially but a negative to Tollens, we can differentiate between the methyl ketone and the other ketone by using their iodoform test. And the methyl ketone will give a yellow precipitate, whilst the non-methyl ketone does not react. But because it had previously given a positive result to the 2,4-DMBH, we can confidently then identify that as the non-methyl ketone. So we've done 3 tests, all relatively simple, and we've already identified 3 of the 8 possible compounds. We then move on to those that gave a negative test, of course, to the 2,4-DMBH. So we're down to 5. And the suggestion then is, let's try using its physical property of acidity or basicity. So let's test them with litmus paper. Of course, the carboxylic acid should give a red coloration to blue litmus paper, and the amine should give you a blue coloration to red litmus paper. Okay, the others should not give any indication of pH at all. Now, physical tests, try backing physical tests like test papers or states with some chemical confirmation as well. So I would say that the amine, you should then go to the next step and confirm the amine is as suspected by reacting it to evolve nitrogen. So if you add nitrous acid, which can be produced, of course, by reacting sodium nitrate 3 with dilute sulfuric acid, both of which were allowed reagents for you, it should then produce nitrous acid, which evolves nitrogen with an amine. You can further confirm the acid then by evolution of CO2, which can be confirmed with lime water, that is your choice. But we know that an acid will evolve CO2 when you add a carbonate or a hydrogen carbonate, of course. So we've now got 5 of the 8 confirmed. Happy days. We then go to the remaining 3 and we boil them with sodium hydroxide. 2 of them will produce ammonia. So we know that the amide and the nitrile will evolve ammonia gas, which can be confirmed using damp red litmus paper, of course. And the remaining compound does not. So 1 will not evolve any gas on that point. For the amide, because we want to differentiate between the amide and the nitrile, both of which give ammonia, you can do it on time because the amide will evolve that ammonia much more rapidly than the nitrile will. But you can also confirm it by the fact that the nitrile gives a white PPT of benzoic acid if the reaction is added to NaOH and then cooled. Okay. And then finally, just to confirm that ester, which gave no positive evolution of ammonia, you can acidify it and then cool it, and the ester gives a white PPT again of that benzoic acid. So in 7 relatively straightforward steps, you've identified all 8, and you've all identified them all chemically as well, which is the key thing here. All possibilities, and therefore it is a really good, sensible plan of attack that you could have used. So if you haven't done that yourself, it is well worthwhile possibly writing up that practical in your lab book so that you've got some real confidence under your belt that you can approach such questions in the exam in May. So that is it for me, and hopefully that gave you some insight. But certainly, if you haven't already been given access to that pre-release information, I would ask for it as a matter of urgency from your centre so that you can start preparing sensibly for that exam. Thank you.